In both 7.1 and 7.2, we are looking at exponential growth and decay functions. So starting off with 7.1 here, we are going to start by graphing exponential growth functions. So I think this is something that we've already talked about at some point within the school year, but let's go through it again. So for an exponential growth function, we have our parent function, y equals a times b to the x power. So this is considered an exponential growth function if a is any number greater than 1, and a has to be greater than 0, and b has to be greater than 1. B is the growth factor, so if it were to be less than 1, then it would turn this into an exponential decay function. So let's start with our example that they already give us the graph for. So how we're going to go about this process is we're going to take the values they give us in our table, substitute those into our equation, and create our graph from there. So this one, the graph's already created, so let's just practice the substitution steps. So for x equals -1, we would have y equals 2 to the negative first power. Remember, when we have a negative exponent, we need to take the reciprocal of our base. So for 2, we're going to flip it, and we're going to make 2 1/2. And now instead of having a negative exponent, we are going to have an exponent of +1. And this is going to turn into +1/2. For 0, remember, anything to the 0 power is just going to give us 1. So 2 to the 0 power is 1. And remember, anything to the first power is itself. So if we have 2 to the first power, we are just going to have 2. And if you guys would like, you can check over here on the graph at -1. It does look like we're at 1/2. At 0, we're at 1. And at 1, we are at 2. So that's going to be our process throughout this entire lesson. So graphing y equals 4 to the x power. Remember, if we're taking a negative exponent, we are going to take the reciprocal. So 4 is going to turn into 1/4. For 0, anything to the 0 power is just going to give us 1. And then 4 to the first power is just going to give us 4. So we can go through and graph this. -1, 1/4, 0 and 1, and 1 and 4. And as you can tell by the shape in the graph, we have an exponential growth function. Remember, key details about an exponential growth function is in the negative direction, it is going to almost touch the asymptote, which in this point is 0. And as it heads to the right, it is going to increase rapidly. All right, so for this last one here, we have y equals 1/2 times 4 to the x power. So we just calculated 4 to the x power, so we can just take those values and multiply them by 1/2. So at -1, we had 1/4, so 1/4 times 1/2 is going to give us 1/8. At 0, we had 1. 1 times 1/2 is just 1/2. 4 to the first power gave us just 4 times 1/2, which gives us 2. And if we wanted to take this one further, if we tried 2, 4 to the second power is 16 times 1/2 is just going to give us 8, because that just about falls in the graph. So let's graph this. -1, 1/8, 0, 1/2, 1, 2, and then 2 is up here by 8, so we will not quite get there. But connecting our points, we're going to have a graph that looks something like this. So that right there is the basics of graphing exponential growth functions. So on page number 2 here, we're looking at translations. So just like translations, our exponential growth and decay functions have translations as well, and they're very similar. So similarly, we have minus h, and we would have plus k. And as it states below, h is our horizontal shift, and k is our vertical shift. So just like a lot of the graphs that we've created so far this year. But one thing that's a little bit different is this time, it's important to realize that they give us a table, and that's going to get us through 90% of our graphing. So really, the translations aren't nearly as important as maybe some other functions. So first of all, if we were to substitute -1 into this function, that would give me 4 times 2 to the -1st minus 1 power minus 3, which that would just equal 4 times 2 to the -2nd power minus 3. 2 to the -2nd is 1 over 2 squared, which would just be 1 over 4. So I've got 4 times 1/4 minus 3. 4 times 1/4 just gives me 1. So I've got 1 minus 3, which is just going to give me -2. So when we substitute in a -1, we are just going to get -2. Okay, for 0, very similar process. 4 times 2 to the 0 minus 1 power minus 3. So that's going to give us 4 times 2 to the -1st power minus 3. 2 to the -1st is just going to turn into 1/2. 4 times 1/2 is just 2 minus 3, which just gives me a -1. Finally, with 1 here, we would have 4 times 2 to the 1 minus 1 power minus 3. 1 minus 1 gives us 0, so 2 to the 0 power is just going to give us 1. So I've got 4 times 1 minus 3, which 4 minus 3 is just going to give us 1. Okay, I do think I want to take this one step further and try with 2, because 2 minus 1 is 1, so I have 2 to the 1st power. 2 to the 1st is just 2. 4 times 2 is 8, minus 3 is going to give us 5, which does fall on the graph, so I felt like it was important to calculate. So at -1 here, we're going to have -2. At 0, of -1, 1 and 1, 2 and 5. And it's going to give us a graph that looks something like this. So one important aspect about translations that we really should keep in mind is our k value. So our k value for this one is -3, which that value is going to act as our asymptote for our graph. An asymptote is a point where the graph is limited, right? This exponential growth graph is never going to touch -3. It's kind of like the baseline. So it's an important check at the very end. Okay, let's go ahead and maybe do 1 or 2 more of these. We'll do one more graph and then we'll go to the application problem. So let's go with number 1 here. So if I have y equals 4 to the x power minus 1, let's see, that'll be my y value. So for -1, I would have 4 to the -1st power minus 1. 4 to the -1st is just 1/4. So y equals 1/4 minus 1. 1/4 minus 1 is just going to give me -3/4. At 0, I'm going to have 4 to the 0 power minus 1 anything to the 0 power is 1. So I'd have 1 minus 1, which is just 0. And then finally, 4 to the first power minus 1. Anything to the first power is itself. So 4 minus 1, which is just going to give me 3. So let's graph this. -1, -3/4, 0, 0, and 1, 3. And finally, we're going to have a graph that looks something like that. Once again, take a quick look at our k value here. Our k value is -1, and as we can clearly see, this graph is never going to actually touch -1. All right, one more quick problem here. So exponential growth and decay is a super applicable math concept, and it totally occurs in the real world all the time. A main application would be in finance. So here I have the compound interest formula, and you guys can read all of the different variables over there on the left. So let's take a look at this problem. So you deposit $10,000 in an account that pays 5.8% annual interest. Find the balance after 5 years if the interest is compounded within the given frequency. So we're going to calculate both quarterly and daily. And actually, maybe we'll just go with quarterly for now, and we can save daily for class. So first of all, let's look at the info we have. So we know that we're trying to calculate the amount, right? So we're trying to calculate A. So I'll start by listing A equals P, which is the principal, the amount of money we started with. And in this case, we are starting with $10,000. So that's going to be our P value. Okay, that's going to be P, which is times 1 plus R over N. So let's look at R. R is the interest rate as a decimal. So as you can see, the interest rate is 5.8%. We can rewrite that as 0.058. Divide this by 100. So we would have our rate 0.058 over N, which is the number of times in 1 year that the interest is compounded. So for our quarterly example here, our interest is going to be compounded quarterly, which happens 4 times within a year. So we'll divide that by 4, but then we have N times T. So N is the number of times in 1 year that the interest is compounded. Well, we already know it's 4, so we'll throw a 4 up there, times T, which is the amount of time in years. Okay, we know that this is compounding for 5 years, so it'll be to the 5th power. So right here, this is an exponential growth function. It's just a little more complex than the ones that we've been calculating. So we can plug this into the calculator. A equals 10,000 times 1 plus 0.058 over 4 to the 4 times 5, which is 20th power. And if we put that in a calculator, you are going to get 13,336.47. Okay, so that is how you would use the compound interest formula. We can maybe do the other one in class together. So please go through, try some of the graphs that we skipped in the video, but we'll make sure to look at them in class. All right, thanks for watching.